What are metals, and how come that they are able to conduct electricity? To understand the properties of metals, we have to take a closer look at their chemistry. Looking at the periodic table, we can observe that most of the elements are metals. Elements are metals at oxidation state 0, so when they are not ionized. Metals have a low ionization energy, meaning that it is easy to remove electrons from the metal, forming cations. An example is the oxidation of a metal when in contact with oxygen. Alkali and alkaline earth metals have the lowest ionization energies, and in atmospheric conditions will always be 1 plus or 2 plus cations. In the p block, on the other side, instead, we will have the most difficult to ionize metals and metalloids that can be found as metals in ambient conditions. Between these two extreme cases, in the central block of a periodic table, we have transition metals. These elements have s and d valence electrons. Lanthanides and actinides have also f valence electrons. Let's keep in mind that some molecules that do not contain metal atoms are metallic too, like sulfur nitride. Transition metals are an interesting and very large group of metals that differ substantially in chemical properties. It is worth defining some general properties. When transition metals are not in a metallic state, oxidation state 0, they are ions with multiple possible oxidation states, a property that is linked to the presence of a large number of valence electrons with similar energies. Vanadium has possible oxidation states of 3 minus, 1 minus, 0, 1 plus, 2, 3, 4, and 5 plus. Let's see the electronic configuration of vanadium 0. Vanadium has 5 valence electrons, 2 in the 4s orbitals and 3 in the 3d orbitals. The 3d orbitals are generally lower in energy when compared to the 4s orbitals. As such, the electron configuration of vanadium is the configuration of argon, plus 3 electrons in the 3d orbitals and 2 electrons in the 4s. When vanadium is oxidized to 2+, the 2 electrons lost will be the 2 4s electrons. When a vanadium 3+ ion is formed, the 2 4s electrons plus 1 3d electrons are lost, and the electron configuration is going to be the one of argon and 3d2. When transition metals ions form bonds, they do not follow the octet rule. They will tend to form complex ions by coordinate bonding. Coordinate bonding is a dative covalent bond where the lone pair of one coordinating molecule, called ligand, is donated to form a covalent bond with a central metal ion. A possible ligand is water that can donate a lone pair present on the oxygen. Vanadium 2+ can form a complex by coordinating 6 water molecules. The formation of complex ions is not limited only to transition metals. Other metals can form them too. Now that we dived a bit in the world of metals and in their chemical properties, let's see what makes a metal conductive: metallic bonding. When we look at bulk metal, like copper, all we see is a block of copper in the metallic state, so oxidation state 0. If we look at the atomic level, we have a face-centered cubic crystal structure of copper. Most metals are crystalline solids. If we look at the subatomic level, what we really have is an ordered set of positively charged copper ions in a sea of electrons. These electrons are coming from the valence electrons of a single copper atoms and are all shared in a free cloud of electrons. Metallic bonding is the electrostatic interaction between copper cations and free electrons. The free electrons are able to move around, and so they are good at conducting electricity and heat. The sea of electrons is very soft, like a pillow, and due to the metal bonding, a metal can be easily pressed into a wire or a sheet. When we look at the material as a whole, we do not speak anymore of orbitals, but bands. We can see a band as a combination of the atomic orbitals for the whole material. Electrons in a material will fill up the many available states inside of a band, in the same way that they normally fill up single orbitals, from the least energetically demanding to the most energetically demanding. The maximum energy that an electron can have in a material at 0 Kelvin is called the Fermi level. The band under that is full of electrons and is the valence band, since it contains the valence electrons. The band above that is the conduction band, since it allows to add more electrons and to pass them around, so it allows to conduct electricity. Electrons can move between these two bands because we are not at 0 Kelvin, so there is some thermal energy. These two bands, in the case of a metal, overlap and create a continuous band. We can see this like a glass half full of electrons. We can pour in or pour out electrons and all is still energetically okay. The more these bands are further away, the least probable is that an electron can jump or move around, because it will need more energy. With a small gap, we will have a semiconductor. With a large gap, instead, we will have an insulator.